Welcome back to SciByte, everybody, where we uncover the mysteries of the universe and the techniques and tools that scientists are using to get to the bottom of it all. My name is Jeremy, and joining me on the Skype line, the same as every episode, is the lovely, the talented, the ever-so-brilliant Heather.
Thanks. Before we get into today's topic, I believe you had a disclaimer before.
Oh, you bet I do. You see, in the past, this show has been really brainy, but let me tell you, the truth of the matter is that science is kind of hard, and you can't really think about it too hard on a regular basis, or you're just going to lose yourself in all the theoretical theories of theories. And, we're going to be doing that on a regular basis on this show, but as we go forward, it's important to keep in mind that science is not always the mysterious happenings of physics and outer space and all that. Science is happening around you all the time, as we speak, in fact. And one of the goals of SciByte in general is to get everybody out there more excited about science in general, more engaged with science in their everyday lives. And that doesn't always mean talking about the complicated things. And I got to be honest, today's topic, when we introduce it, you might think it sounds a little dumb, a little silly, but I bet you that there's stuff that we will be discussing today that even you brainy people smart enough to tune into this show don't know that much about. Heather, why don't you lay it on us? Just introduce today's topic for him.
Sure. Today we're going to look at the science of barbecue. Take a look at fire, cooking, plus we'll apply our science filters to the great propane charcoal debate.
And as we get into the meat of this tender subject, we hope that all of you chew on all the delicious morsels of wisdom that we've been marinating on for the past week. You like that? I had some complaints that last week's show didn't include a pun, so I figured I'd make up for it. So as we get into today's topic, I just want to say right up front, fire is awesome. I mean, of course, you have to treat it with respect and all that. It's a powerful force to be reckoned with, but it's also science in the happening. I mean, when you get right down to the basics of what fire is, it's awesome. Now, I realize that fire has been around for, you told me before we started the show, something like the earliest record, it was like hundreds of thousands of years BC.
Yeah, the earliest cooking fires.
Right. The humans have been using it to cook with for that long. So really, at this point in our lives, we should know how to use it, right?
Yeah.
Well, not exactly. I mean, that's kind of saying like your grandma knows how to use the smartphone you gave her for Christmas. I mean, just because you have a tool doesn't mean you're an expert. In fact, it's even been as recent as ancient Greece that we had completely misconceived what fire is.
Yep. The ancient Greeks considered that there were 4 elements to the universe: water, earth, air, and fire.
That makes perfect sense.
Yes. To them, everything was made up of one of those 2 things or a combination of them.
So they actually considered fire as almost like a form of matter to a certain degree. But we now know, because we're smarter than ancient Greeks, that it's not matter at all. Fire, what exactly is fire then?
Fire is simply a visible effect of matter changing form. It's a part of a chemical reaction between the oxygen in the atmosphere and some sort of fuel, like wood or gasoline. When you heat that fuel to its ignition temperature, you set off a rapid, self-sustaining, oxidizing process that causes energy to be released in the form of heat and light, what we see as fire.
Let's talk a little bit about the fact that it's self-sustaining and how that exactly happens. I mean, in order to get a fire going, everybody knows you have to light it. You have to excite the molecules, basically, to a point that they will combust. But by doing that, you're also releasing what many people call volatile chemicals from the basic fuel source that then, if they're hot enough, caused by the original fire, can then ignite as well, causing, just like you mentioned earlier, a chain reaction.
Now, as long as you have fuel and oxygen, the fire will be self-sustaining. Now, some fuels are more flammable than others. Anything with carbon and hydrogen, which recombine with oxygen fairly easily to form carbon dioxide, water, and other gases.
The molecular bonds come together very easily in those particular types.
Yes.
Now, there's a quote that I heard in a video that I'm probably showing you guys right now, that a large-scale forest fire can release as much energy from these molecular recombinations and everything. In 15 minutes, a large forest fire can emit as much energy as the bomb that blew up Hiroshima, as an atomic bomb in 15 minutes of a forest fire. And actually, when you get right down to it, isn't that kind of what it is? I mean, the molecular bonding is the same as what happens in an atomic explosion, only on a much different scale.
Well, it's atomic bonds versus molecular bonds.
Right.
So a little bit different, but you're still releasing energy in some form or another.
Now, everybody knows that besides being this awesome force that can destroy things very easily, yay for fire, it's really good for cooking with. And today's episode is going to be called The Science of Barbecue, so we might as well get into exactly how fire is used to cook things. We all cook things, right? Right?
Yeah. When heat is used in the preparation of food, it can kill inactive, potentially harmful organisms such as bacteria and viruses. So it's making our food a little safer to ingest. And it's changing the form of it.
And delicious. Why don't we talk a little bit about one of the primary forms of cooking, one of the chemical reactions? I mean, there's basically two that are most commonly talked about. There's caramelization, which is the reaction of sugars with other sugars. When you get them under heat, they interact with one another. I don't want to go too much into that because I don't entirely understand it. But the other one is what we're going to be focusing on today's episode, is sugars with amino acids. This is called the Maillard reaction. And the reason that this is the one we're going to be talking about is because amino acids are what's in barbecue, is in meat. Yes. Proteins and amino acids are basically what your meat's made of. So when you combine sugars, like you'll find in barbecue sauce, with heat and amino acids, you get the Maillard reaction. And this is, why don't you give us kind of a sciencey explanation on what this results in, what you can see this as when you're cooking on the grill.
You're cooking on the grill. That's what gives, the Maillard reaction is what gives you that brown outer, extremely flavorful layer of the meat. It's recombining the proteins. The cooking itself is making the protein chains bunch up, and that bunching sort of expels some of the moisture from the meat, which dries it out and kind of shrinks it down. So that's why your meat kind of gets smaller and weighs a little less when it's cooked.
And that's also, you gave me a great cooking tip in our show notes here. That's you can also tell by the density of pressing on your meat while you're cooking it, how far along it is. Yeah. Like the more squishy your meat, basically, the less cooked it is. And that's all controlled by this Maillard reaction and the evaporation of excess water and the cooking away of fat within the meat that you're cooking on the grill. Now, the details of that are as follows. If you're looking at, let's see, why don't you point on your hand, because I'm not sure exactly what you were talking about, that there's a fleshy part under your thumb that will indicate the...
Okay.
Yeah?
Let's find a spot for my thumb. Okay, there we go.
Rare to medium rare is right there. Point.
Rare to medium rare is right about here, the fleshy part underneath your thumb.
And
so you can kind of press that and you can kind of feel it's a little squishy.
Yep.
Medium, go to like the middle of your hand. So it's a little less squishy, but there's a little bit there. And then medium well to well done is near your finger knuckles. So it's that hard, not a lot of give to it.
There's actually a school of thought out there that says that you shouldn't be cooking your meat all the way to medium, up to well done. Now, it's not actually, it doesn't really have anything to do with how well you cook your meat on the inside or anything, but the problem is, particularly with barbecue, that in order to get your meat to the point of being well done, you end up charring the outside of that meat. And, I love the taste of burnt meat. I will just come out and admit that. Getting my meat well done with that little black film on the outside that's sometimes made up of, my mouth's watering just thinking about it, but apparently cancer is delicious because that black stuff is made up very highly, of carcinogens that can increase your risks of stomach cancer by up to 3 times versus just eating meat that's not charred. So, I mean, it's worth keeping in consideration. Like I said, I got to wipe my lip on it, though. I just love it. Apparently, cancer is delicious, and I'm probably just going to keep risking it.
Well, and that applies to anything touching the surface. So if marinades can, it kind of creates a buffer between them and the hot surface.
Right.
So that kind of gives you a little bit of leeway.
Kind of a thin layer of the marinade can protect yourself from it.
Yeah, you can. Now, you can still, of course, you can set things on fire if you cook them too long.
Well, and also your meat itself or whatever you're cooking on the grill can potentially release chemicals that if your fire's hot enough, they can ignite themselves. I mean, that's basically what happens if you can get your barbecue too hot, guys. You can. It can be done. Actually, why don't we talk a little bit more about the actual process involved in the fire? And we've covered a little bit about the meat. I got to get off the topic because I'm getting starved here. But, there's a big debate out there, huge debate about, everybody talks about the difference between cooking with charcoal briquettes or propane gas. We're going to talk about that a little bit. We'll give you some of the science behind one and the other. But first, I thought it was interesting if we can cover some of the history of the charcoal briquette itself.
The charcoal briquette was first invented and patented by a person named Ellsworth Zwoyer in Pennsylvania in 1897. But it was kind of slow going, not a lot of interest in it until the 1920s when Henry Ford decided to use recycled wood scraps from
good
his
old Hank
automaking.
Ford.
And some people even think that he's the one that created it just because he made it so popularized.
Right. He gets credit for a lot of things, doesn't he?
Yeah, he deserves some of it.
Now, but how is a briquette actually made? I'm going to interrupt you a few times when you explain this because keep in mind that briquettes of this nature have been being made since 1897, and some of this is really sciencey, people. So pay attention.
So we start the process with sawdust and wood chips, generally from lumber mills, unloaded. They mix it up in, with big bulldozers, and then they'll take those along conveyor belts with big electromagnets to pull out any, metals or anything so you don't ruin some of the machinery as it goes through.
This is one of my first interruptions because keep in mind they've been using magnets to rip the metal parts out of this since before the 1900s. I realize magnets have been around a lot longer than that, but this just sounds sciencey to me. I'm sorry. Okay, go on. So after they've stripped out all the metal and they've shaken out all the big bits of it and strained them out, so they're left with just this mulch.
Yes.
What happens next to that mulch?
Then the mulch goes into a long rotating dryer, which heats it to about 1400 degrees for 4 minutes, but sealed from oxygen, so to prevent it from actually catching fire.
The entire oven itself is completely sealed off from oxygen?
That is correct.
How did they manage that before 1900? Okay, no more interruptions.
Well, I mean, you can completely seal it from oxygen, which we can do much better now, sealed in barrels and stuff. Mm-hmm. But you can just, what they used to do is just take chunks of wood and then bury them.
Oh, so they just put them under the ground while they heat them up.
Yeah.
So there's no air down there, or it gets quickly displaced by things catching fire.
Yeah.
Until there's no more oxygen to,
You may not be able to eliminate the oxygen, but you can decrease it significantly.
Sure.
So in the modern process, now we have this heated sawdust mulch, and then we have anthracite coal is added. So that raises the burning temperature.
So it takes a higher temperature to actually ignite this final product.
That is correct.
Okay.
Then from there, they add lime, and the lime is actually kind of talks about a lot of different things.
I was just going to say, isn't lime usually poisonous?
And the term lime is really just a general term for any calcium-containing inorganic material. So the lime that they add to the briquettes is that's what makes them white when they burn.
Oh, right, because I get it. Because when you light them on fire, you can't always see the fire. The fact that all of these impurities are stripped out of charcoal briquettes when you burn them, if you didn't have some way to tell that they were burning, which is done with the lime, you might not be able to tell that you had actually lit them on fire, that there's fire coming off that.
Yeah,
and heat.
You can't really see the fire. There's no smoke to say.
Right.
So it's a very quick visual confirmation that, yes, briquettes are on fire.
Boy, I'm glad they thought of that.
I'm sure it didn't take long to figure that we need an extra safety precaution here.
Yeah. After they've mixed that lime up, is that it? Is that basically ready to go in the bags?
Not quite. Then they add cornstarch, which is blended into the ingredients to make a binder, sort of to help hold everything together. So
they don't just fall apart when you light them on fire.
Yeah. Well, from then, they put them into a press, and that gives them their briquette shape. And it only takes a fraction of a second to compress them in there.
That sounds really dangerous, but awesome.
Yes.
Now, at this point, are they ready?
Almost. At this point, they're still about 35% moisture, and they're soft. So if you picked them up, you could actually kind of squish it.
Oh, well, that is completely
like
unacceptable.
Stuff. Yeah. So from there, they go along a 250-foot drying tunnel where they're heated to about 280 degrees for 2.5 hours. This kind of finishes the baking process, hardens them up. The moisture content goes from about 35% down to 5%. The lower moisture level gives a much better burn.
I want to sidetrack here for just a minute before we get into talking about some other fuel sources that you can use in your barbecue. I want to talk about starter chimneys. This is something that I have only recently come across. My little brother actually introduced me to these, and I watched a whole introduction to them on YouTube in preparation for tonight's big show. If you guys are not using a starter chimney, I highly recommend it. This is you need no direct flame on your coals. They get nice, evenly heated before you apply them to your barbecue. And there's an added benefit. I'll circle back to that when we're talking about propane. But I just wanted to introduce, if you've never seen a starter chimney before, this is a must-have if you're a fan of charcoal briquettes.
Oh, yeah.
Now, but speaking of charcoal briquettes, this actually just gets me wondering, because I live in the woods. There's a lot of trees around. I can just cut down and light those on fire, can I? I mean, what's the difference between using all this complicated stuff that goes through long drying processes and is mixed with lime and all blah, blah, blah? Why can't I just throw some wood in there? What's the difference?
Well, you certainly can. I mean, obviously, wood burns, but freshly cut wood contains a lot of water. Sometimes more than half of its weight is actually water. And then watery wood doesn't really make for efficient cooking. The flame itself is cooler, it takes a lot more energy, and it can contain sap, these volatile hydrocarbons in the cells, which releases smoke. So you have a lot of smoke, and depending on the type of tree you're using, then that smoke will sort of flavor your food, and you may not want wintergreen pine taste in your steak.
But you might. I mean, you got to keep it in mind. Actually, I've heard of people that use wood chips, like mesquite smoked bark chips on top of their coals to give it a nice flavor in their barbecues. But okay, we're talking about individual different types of fuel. Let's go ahead and start working our way into the great propane debate. But before we get into that specifically, we covered how briquettes are made. Let's talk a little bit about what propane is.
When you have the tank that you pick up from the grocery or you refill, it's liquid propane. And that's the majority of gas grills are liquid propane. It is a fossil fuel just like oil or natural gas.
And where did propane actually come from? Is this something that somebody actually set out to invent in order to put it in our barbecues?
Well, it's not something that was necessarily invented, but it could be found. Initially, the natural gas industry was having problems with these extra compounds contaminating it. It's propane and butane. They're much more easily evaporated. They have a higher vapor pressure, which means if you are transporting natural gas with propane and butane in it, then you have to have a much stronger container and has to be able to withstand higher pressures.
Well, I can see how that could have been inconvenient when they were first refining fuels.
Yeah. So a man named Dr. Walter Snelling began experimenting it and condensing with these waste materials as they had, about 1910.
Oh. So that means that actually propane might technically have been around prior to the widespread adoption of charcoal briquettes, at least in some form. Maybe not in our barbecues that you could buy at the supermarket and everything like that, but it's been around.
Yeah, he was experimenting with it in 1910. By 1911, he had samples of propane and butane. He had visions for ways to storage and to have a storage and distribution system for these fuels. And by 1913, he was granted a patent for these kind of gases, for his method of producing them.
Now, you mentioned earlier that in order to produce propane, it actually is a byproduct of other forms of refinement, but you can actually do it on purpose as well. Now, the chemical processes included in this also result in things like you mentioned butane, but there's also methane as well. What exactly is the difference between all these different kinds of gas, and is there a way that people can control making them, or do they just kind of have to sort them as they're made in the refinement process?
The refinement process is more about sorting them. They break down. You can sort of control how these kind of things break down, but really it's more about holding a certain temperature to kind of get the best mix that you think you're going to get, and then just spilling this gas off or that gas off through separations and temperature changes and things like that.
Now let's talk a little bit about that temperature change, because this is actually what makes the chemical reaction that results in pretty flames and destruction of forest fires and all that stuff. Is all of these different types of natural gas, propane, methane, butane, they are made up of chains of hydrocarbons, which is nothing but carbon and hydrogen in different amounts. Now the whole process of burning these is the chemical introduction, the molecular introduction of oxygen into their mix. And when you get them hot, they start to excite to such a point that some of those carbons can see the nearby oxygen that's sitting right over there, and they go, "You're my new buddy," and they switch around. That is the entire process. Now, is there any one of these particular three fuels that we've mentioned, methane, butane, and propane, that burn easier? Do they have lower ignitions temperatures or anything like that?
Now, I don't actually know the answer to that, but I'm sure any of our viewers can look it up, make comments about that. But I know it doesn't take a lot of heat to start up propane.
Well, yeah, it's nothing more than a little clicky thing, the little knobby thing on the front of your... What is that thing, anyway?
The little clicky thing is a piezoelectric crystal.
A piezo... Excuse me?
Piezoelectric. It means that when you apply pressure to them, there is a charge separation within the molecules of the crystal themselves, and you get a voltage across it, so you get a spark.
Now, I'll be honest, I did not have any idea. I thought that was flint and steel. Maybe that's just the monkey in me speaking, the caveman out there, but I thought that the little clicking was flint and steel igniting the gases in there.
No, it's actually essentially like a little hammer hitting a little crystal, and then that has leads off of it, which can spark, and then that sparking ignites the gas.
You know, if you guys have never heard of this particular reaction, and I hadn't actually before we started doing our research for this particular episode, I'm going to put some links in our show notes to a few different videos explaining kind of how it works. It's pretty complicated when you get right down to the very molecular structure, but the gist of it is when you squeeze a crystal, a certain type of crystal, you create voltage. And I didn't know that this existed. So inside your propane starter, if I'm understanding correctly, is just a tiny little crystal that gets hit with a hammer, but that's the same thing as squeezing it. It's just a momentary electrical discharge, which is usually enough to, just like you said, ignite propane. And let's be honest, it's also a lot easier to just start a propane grill, which is probably one of the parts of the debate that people get down to when they're talking about charcoal versus gas. A lot of people argue about which one is better than the other in terms of taste, but there's also a convenience factor. It's so much easier to start a propane grill. I mean, just even a lazy monkey with half a brain could do it.
You push a button and come back in 10 minutes and magic happens.
Exactly. But since I just introduced it, why don't we get a little bit into the topic of the taste difference between the two. Now, one of the primary arguments that people in favor of cooking with charcoal mention is that propane, when you light it on fire, releases water as a byproduct of it actually burning. It releases H2O, hydrogen and oxygen in pairs, and that can create, so they say, and I want you to tell me whether or not this is true or just some urban legend, but they say that creates a thin layer around your meat that can prevent it from cooking properly. Is that true?
Well, the propane reaction does release water in it, but it may surround the meat slightly. But that barrier, that slight moisture barrier, could help with the charring problem that we were talking about earlier, too.
Where, like I mentioned, if you get the char, it's a carcinogen, it's not good for you. But you know what? That's the other side of the debate. Cancer is delicious. I'm saying it for the third time in this episode, but that's the problem, is that people that cook with charcoal frequently enjoy that flavor, regardless of the bad side effects to it. Additionally, if you cook with charcoal, you're more likely to release smoke. I know that, as we said earlier, when charcoal briquettes are created, most of those impurities are removed from the process, but you don't really get all of it out, except maybe with the really expensive brands, but those aren't worth using anyway. So the smoke from those charcoal briquettes, it flavors the meat slightly, so there is going to be a difference. I think in my personal opinion, and you can correct me if there's some sciencey reason for me being wrong on this, but it really comes down to personal taste. I mean, literally speaking, personal taste, doesn't it?
To some degree, yes. There was a taste study done so that the people didn't know which one they were getting. And when they were presented with hamburgers and presented with steaks, and when presented with the hamburgers, no one could tell the difference between charcoal and propane. Now, with the steaks, they could tell a difference. They said that the charcoal steak had a more distinctive smoky flavor.
Which just goes to further prove the point I've been making this entire episode. Cancer is delicious. I don't really support that, people. I'm not making light of this terrible disease, but come on. The black stuff on the outside of your steak, who doesn't love that? Now,
I don't love that.
You're too good for it. let's talk a little bit about, before we sign off for the day, we're pretty much covered all the science that we've got to cover in today. But, I mean, we're talking about barbecue. We might as well cover some more cooking tips, right? You've got some here about cooking ribs.
Now, if you've ever just taken ribs and thrown them on the grill, you know that the fats will drop down onto the coals or onto your propane, and it'll cause flare-ups. And now flare-ups, not so good for your meat.
No, and actually the reason that they're not so good is because if that fire actually engulfs your meat, it can burn it, it can char it, just like we were saying earlier. I mean, it takes surface temperature of 400 to 500 degrees to create that char. But if you're getting flare-ups, it's much easier to get that unfortunate black coating that is so good. If you want to avoid that.
Now, there is a way to avoid that. Now, you may have heard to boil or simmer your ribs. Then there is a difference between boiling and simmering. If you boil it, it will rapidly denature or unfold the structure of the proteins, and that can make them a little bit tough and chewy. But if you just simmer them, then you can reduce the fats, reduce the flare-ups. And
isn't that also going to slightly alter the actual flavor of your ribs, though?
No, it might, but if you cook it you can pre-flavor them before you simmer them. You can cook them. Some people cook them in sort of alcohol or beer or something to sort of add flavor back in.
I am with those people.
It's like a lot of cooking. It's sort of a give and take. You can reduce the flare-ups and still cook them on the grill, so you'll add back in that flavor, and you don't have to worry about the flare-ups as much.
Now, what about steaks? There's not usually quite so much of an issue with flare-ups. They're not quite as drippy as ribs. Or is there any good advice that you might give for cooking a steak on the grill?
Sure. Steak, if you leave it out you don't take it straight from the fridge to the grill, then you leave it out on the counter. You're not going to leave it out for a long time. Nothing any more than an hour, because then you start getting those bacteria and the viruses that can grow. But if you leave it out for a little while, give it a little bit of time to get to acclimate to room temperature, then it's not as much as a shift, and it'll cook much more evenly.
Oh, the whole way through the meat. So you don't have to worry so much if you want a well-done steak, but you want to avoid char. That's probably a good tip for doing it. Get your meat to get comfortable at room temperature, and you'll be able to cook it more evenly. Well, that's great. I wish we had more tips about like the best barbecue sauces out there, but I was trying to get us sponsorships for this show. They didn't come through in time. Now, another thing we don't actually have for this show, unfortunately, is, when we cover science on other topics, we typically include a lot of social links about things that you can follow on Twitter and cooking, science-y projects that you can find all over the internet. We don't really have anything out there. I'll be honest, I looked, and the only ones that I could find were like sponsored, like the Heinz Twitter or things like that, and that's not what you people want. You want real science, and you want real advice, and not just some brand named sponsorship stuff like that. So none of that in our show notes. But speaking of fire, I don't know if you guys have noticed, but summer's coming around, and that means that we're going to get a lot more exposure from that great big ball of fire up in the sky. I think it's behind me actually right now. But the sun. Next week's episode is going to focus all on the sun, about solar storms, coronal mass ejections, which you just told me recently. We just had a big one like a couple weeks ago that was like,
yes, we did,
really prominent. So we'll talk about that. We'll talk about solar winds maybe a little bit, all on next week's episode of SciByte. So if you're interested in that, if you have any information that you'd like to make sure gets into the show, I would highly recommend anybody that wants to have their voice heard, head over to jupitercolony.com and join our active community of science nerds over there that are talking about all sorts of different topics. We've already started farming some subjects from the forum itself that we'll probably talk about on future shows, but for now, the sun will be the focus of SciByte Episode 7.
Also, don't forget our Twitter accounts. I am JB_MarsBase, or you can leave a comment on wherever you're watching this video, or even send us an email at SciByte@JupiterBroadcasting.com.
Well done, Mars. I would have completely forgot. I clearly already had. But she told you her Twitter, so you can also follow me as well. I am JB Jeremy. But really, if you're interested in science, you should be following her, not me. All right, that's officially it. I'm done, right? I didn't forget anything else?
I think we're okay.
Okay, well, join us next week where we'll talk about the sun. And until then, everybody, have a delicious summer.